Well, thank you for that kind introduction, John, and thank you to the organizers for inviting me. The timing is good here because a lot of the questions that came up after Dave's talk are exactly the things that I'm going to be talking about. And in fact, I wish I could change my talk a little bit now, and given what Dave did, because I'm going to talk about modeling, but modeling can take different forms, and there's a kind of modeling Dave did, which I would call good modeling, which is constructing models that you don't believe. I mean, clearly, Dave doesn't think that the data were generated exactly from that model, and yet the structure of the model helps you learn stuff about the data. Versus the other type of modeling, which is, I have to say, statisticians are very guilty of, which is write down a convenient model based on mathematical convenience, and now act as if that's exactly the truth, and everything follows from that. So I'm going to, let's see. So first I will say just a few words about what's the difference between ML versus statistics and econometrics. Dave already said stuff about that. Then I want to talk about just a few examples of what people, it's hard to say what's machine learning and statistics these days, but I want to talk in particular about just a couple of examples, the Lasso and random forests. And then what I really want to focus on this talk is exactly what, I forget who it was, someone in the audience asked about, which is inference. You do these high dimensional things, how do you actually get confidence intervals and do inference? Very active area right now. There's many different methods. If I have time, I'm going to talk about six of them: debiasing, conditioning, uniform methods, sample splitting, subsampling, conformal inference. I probably won't have time to get to all these. When I was young, I could really plan my talks well. As I've gotten older, I'm just like terrible at this, so I don't know how much I'll get through here, but I'll certainly make my slides available for anybody who wants them. If I have time, I'll say a few words about causal inference. I'm not an expert in causal inference, but I have worked on it a little bit in the past, and I know that's something in economics that's obviously of great interest. So I may have time for that, I may not, but I believe Susan and I think Victor, is Victor here yet? Victor hasn't shown up yet, but I think their talks are going to be about combining causal inference and machine learning methods, where I would say machine learning just means high dimensional regression. And in particular, Victor has recently invented, I saw a paper last week, a cool term called double machine learning. So a lot of this, he certainly has picked up on the key fact of machine learning, which is coming up with cool names. Now, here's a warning. All right. I'm extremely opinionated. All right. And I have a very biased view about things, and it's controversial. I'm an outlier. And I want to read this quote. David Friedman is one of my intellectual heroes. He passed away a few years ago. Great statistician. He says, investigators who use regression are not paying adequate attention to the connection, if any, between the models and the phenomenon they are studying. And by the time the models are deployed, the scientific position is hopeless. Reliance on such models is Panglossian. So I saw that. I said, I better look up Panglossian. So it means characterized by or given to extreme optimism, especially in the face of hardship or adversity. Friedman was a total, David worked on mathematical statistics and did, beautiful stuff. But when he did applied statistics, he just didn't believe in models at all. He just thought models were completely bogus. And this is what he was referring to. I'm also skeptical of assumptions, and a lot of my work recently has been about trying to do high-dimensional inference without assumptions, or trying to weaken assumptions. But again, I seem to be an outlier here. But I do want to make this distinction between making assumptions, writing down a model, and then acting like, now I'm going to estimate the treatment effect to within 3 decimal places, that kind of thing, versus, again, what Dave was doing, which is, no, this model was just to help me guide my exploration of the data and to learn patterns in the data and so on. So I really should have made that distinction here because I didn't do it, and I wish I had given Dave's great talk. But I'm sort of giving this David Friedman point of view. So what is ML? Well, the joke I always tell, so as John pointed out, I have a joint appointment in ML and stats in Baker Hall, and ML is in Gates, and I always reuse the same joke. Every year I tell these students in both, and I start with the same joke. I hope they probably have all heard it by now, but I say if you're doing statistics in Baker Hall, you're doing statistics. If you're doing statistics in Gates, then you're doing machine learning. It's really very little difference in some sense between the two fields. although that's not quite true. But I would say in machine learning, assumptions are pretty light. So when you make assumptions, you don't necessarily believe them. They're just a tool towards an end. And a lot of the times, the goal is high-dimensional prediction. Not always, but that's often a goal. Statistics, I would say, the assumptions tend to be much heavier. And we're interested typically not in just prediction, but also inference. Things like we were talking about at the end of Dave's talk. And now, I'm not an economist, but I'm going to go out on a limb. I'm going to go out on a limb and say that assumptions tend to get heavier. You start to put in instrumental variables and ignorability assumptions and so on. And it's prediction and inference, and of course causation is the big thing. And of course this is not just economics, but I would say epidemiology and biostatistics and so on. And that's not meant as a criticism. It's meant that's what you have to do to answer the questions that are the questions are more difficult, I guess is the way to say it. So let's work up to this. Let's just go back to the pure prediction model. We're just going to have a bunch of data. They're pairs, x's and y's as usual. Very important is, didn't have time to talk about, won't have time to, is I treat the x's as random. I'm very against treating the x's as fixed, as many statisticians do. And there's a wonderful paper by Andreas Buya and Larry Brown and a bunch of guys at Wharton called The Conspiracy of Something or Other. It's in statistical science, and it makes a very, very strong case for why it's totally misleading to treat the x's as fixed in regression. I won't have time to go through it, but I'm a strong believer that we should treat x as random. We're going to have the covariate is in d dimensions, and of course what makes things interesting these days and makes things difficult is that d could be much larger than n, the sample size. D for dimension, n for sample size. Y could be, say, a real value thing, regression, or 0-1 classification. I'll just focus on regression, but everything I'm saying could apply to classification as well. There'll be some unknown regression function, mu of x, the mean of y given x, which we don't know. And if I had to summarize machine learning, at the risk of being making somewhat of a cartoon, you get a new pair x and y, and you just want to predict it well. So you're just going to look at y minus your prediction mu hat of x. And the key thing in machine learning is that to do that, you're balancing bias and variance inevitably. It all comes down to bias, balancing bias and variance. In contrast, as you all know as economists, balancing bias and variance is a terrible thing to do in causal inference because bias kills you. You won't get a correctly centered confidence interval. All the stuff about influence functions and correcting bias and so on in semi-parametric inference is about getting rid of the root n bias because otherwise you can't even get a correct confidence interval. So bias is much worse for causal inference, and I think that's a kind of interesting mathematical distinction. In fact, most people, I would say, in the general machine learning community have no clue that you should do something other than balance bias and variance. All right, so there's a billion prediction methods now and support vector machines, this and that. I just want to mention a few. I'm going to mention three. The Lasso, I'm sure you've heard of all of these. The Lasso, which is just a way of doing high-dimensional inference. Random forest may be less familiar if you don't have experience. And I'm just using it because it's very popular, and it's considered, I think, the best off-the-shelf non-parametric prediction method these days, as far as I know. Like if you just have to run a quick prediction method that's very non-parametric, random forest. And actually, Susan's done a lot of work recently about importing the random forest idea into causal inference. And then there's deep learning. Everybody's heard of deep learning. Depending on who you ask, it's the biggest breakthrough in the world, or it's snake oil. I don't have an opinion about that. No one seems to really understand it deeply enough to say. I'm not going to take an opinion on that. Let me just remind you quickly what the Lasso is. All right, so the Lasso, you just take the usual sums of squares, and instead of minimizing that, we add a penalty, and the key, of course, for the Lasso is an L1 penalty, not an L2 penalty. This is the L1 penalty. Can anybody even see that laser? Yeah, okay. And so this is now so popular that it hardly needs an introduction. I would say it's, as far as I know, the most popular high-dimensional regression tool now. And why does everyone use it? I think there's a few reasons. It's convex. The problem is convex, which means you can find beta hat quickly. The resulting beta hat is sparse, which is what we want. We want a typically we want to zero out many of the parameters, and this does estimation and model selection for you simultaneously. You get a sparse estimator. And quite frankly, you can prove things about it. If you want to understand its behavior, because it's the solution of a convex problem, you can prove things. Forward stepwise regression, I actually like that because I can even program that myself. But it's much harder to prove things about greedy methods. So I think that these are some of the reasons why I think the Lasso has become the method of choice. There are questions. What does beta mean? And this is a big issue about the difference between machine learning, I think, and statistics. And I'm going to talk a little bit about the interpretation of the parameter, I think is quite important. How do you choose lambda? The typical answer would be cross-validation. Cross-validation balances bias and variance, though, which may not be what you want to do. And how do we do inference? And that's what most I'm going to focus on in this talk. Let me just do a quick description of random forest in case you haven't seen it. First, you start with a regression tree. What's a regression tree? Just a piecewise constant estimator done by recursive splitting. So you can do it for regression or classification. So actually, this just typical picture would be you take a variable, say x2, and you split it. You split to the left and to the right. Then maybe you'll take x1 and split that. And so you split recursively. Here's x1 and x2. That just ends up you're splitting variables. You just end up with a piecewise constant estimator. It's actually, I think, one of the nicest and simplest non-parametric predictors because it's very simple and interpretable. And well, as I say, I think Susan, will you talk about this? Yeah, so Susan will talk more about this. But these are very, very popular non-parametric tools. Whether you call that non-parametric statistics or machine learning, you can call it either one, I think. And forests just combine a bunch of these. So in forests, you typically draw subsamples from your data. And for each subsample, you fit a tree. And usually, you also take a subset of all the covariates at the same time. And then you get a bunch of trees, and you just average them together. And this just works remarkably well. There's been some attempts to explain why, but I don't think there's really a convincing explanation yet. But it just works well in practice. There's just no doubt about it. So it looks like this. You have an observation. Now you have a bunch of trees. And you're going to feed this down each tree and combine the output. And so it's a pretty, it's an interesting thing because it's very effective. But now we've lost the simplicity and the interpretation and so on. And there's sort of a conflict there between interpretability and good prediction. All right, so the question is, if you do any of these things, random forest, Lasso, whatever, how do we do inference? Well, before I say that, do you want to do inference? So I would really say if you're in a pure machine learning problem, it's kind of irrelevant, right? If all you're trying to do is you have a program that's deciding whether my mail is spam or real, I don't really care about confidence intervals. I just want to make sure I'm reading, the mail that I'm supposed to be reading. So in some cases, of course, the answer might be we don't need to do inference. So I'm going to assume, though, we do want to do inference. There's obviously cases where we want to do inference, and as economists, that's an easier sell than maybe to a machine learning crowd. But what parameter are we actually estimating? There's actually several different parameters, and a lot of the work on what's called post-selection inference or selective inference in statistics in the last 2 years has been focusing on even what's the parameter. Some of these papers are estimating different parameters. So I would divide it, I'm going to divide it into 3 groups. There's something I would call the true parameter view, where the assumption is that the true model that generated the data is linear. So, and remember, this is a high-dimensional linear model. Well, in that case, beta is pretty clear, right? There it is. It's the thing in the linear model. I have to say, I think this is pretty much a bogus assumption. When I was a student, and I learned linear regression from one of the greatest applied statisticians in the world, his name is David Andrews. Many of you would not have heard of him. And this is in the low-dimensional days. And I remember when he taught it to us, day one, he put down the linear model. He said, we're going to use this to fit the data. He says, but for God's sake, don't believe the model. I mean, that was like, day one was the model's wrong. And now I find, people are writing down these high-dimensional models and acting as if the model's true. And I understand for theory, maybe we don't have a choice. But for making policy decisions and things like that, I find that quite worrying. Why would the true model be linear? And you can't, by the way, in high dimensions, none of these assumptions are testable. If they were, we wouldn't need to regularize, right? We regularize to take an ill-posed problem and make it well-posed. And if you could test the assumption, it wouldn't have been ill-posed to start with. which doesn't mean you shouldn't make this assumption. It just means, you know, about how to interpret it. But there's a different point of view which has been used, I would say, throughout the history of statistics, but it's become much more popular. And I have some papers on this, and there's these guys at Stanford doing what I'll call the Stanfordian view of inference, which definitely take this point of view. And also there's this group at Wharton who's been doing a lot of this inference, and they're also taking this point of view. So we're all in agreement on this, which is we don't interpret the beta that comes out of regression as any sort of true beta. And so this is kind of comports with, in some sense, what Dave was saying. We just view it as, in some sense, the best approximation. So formally, if you give me a new y and an x, I can look at the prediction error and ask, what's the best linear predictor? That's certainly a well-defined quantity without assuming the truth is linear. So we don't assume mu is linear, but we still talk about the best linear predictor. Or in other words, it's just the projection, right, onto the set of the space of linear predictors. So that's called the projection parameter. And a lot of the new inference stuff takes the point of view that the model is not linear, but we can still try to do inference for the projection parameter. And things get more interesting because when we do the lasso or we do something else, we're going to do model selection. So we're going to choose a subset of the variables based on the data, of course. This is going to be a data-dependent selection. And now beta sub s is a really interesting thing. It's the projection. It's the best linear predictor on the 10 variables I selected. What makes that really interesting is not only is this a projection parameter, but now the parameter is random because s is random. So now we're doing inference for random parameters. So the data are random and the parameters are random. And all right. That random parameter. And it's also, by the way, at a technical note, it's not a smooth parameter. For you know, I'm sure a lot of you are familiar with the bootstrap. You would need the parameter to be Hadamard differentiable. It has to be smooth. This is not, because typically model selection procedures are, you know, very sensitive to small changes. So we can't just do the bootstrap or some typical procedure. There's another parameter, though. And this is the one I've been writing papers about with my colleagues at CMU. I'm sure we didn't invent it, but we invented a name for it called LOCO, because it's a little bit crazy. It stands out for leave-out covariates. It's very trivial. So there's an archive paper about one approach to dealing with LOCO parameters. And we have another paper we're about to finish, I'm going to say next week, that will go in the archive. And it's just very simple. And again, I'm sure lots of people have been doing this for years, which is, let me explain what this equation is. I'm going to, let's say I fit something. It could be a random forest, could be the lasso. So I'm looking at a new pair, x and y. This expected value is just over a new pair, x and y. And I'm looking at the prediction error. So that's y minus my, why did I put mu transpose? This should be mu hat of x. Sorry about that. This is just my prediction of a new pair. Now I'm going to say, suppose I didn't have access to covariate J. Maybe that's say unemployment. I don't have access to unemployment. How much do my predictions change? And so that's a measure of variable importance. So I'm going to I'm not taking the I'm not zeroing out that thing. I'm rerunning the entire process. Whatever I did, the selection process, the variable selection process, the model fitting without that variable. It's as if I didn't know about variable J. And that gives me a new predictor, which is, I think this has died. But anyway, it's this one. And now I'm just looking at the difference. And so that has a very clear interpretation. It's just, what is the prediction inflation? How much extra prediction error would I pay by not having access to variable J? And what we like about this is this has a clear interpretation without resorting to linearity or whatever the model is. It just says, how much price do I pay in prediction by not knowing this variable? That's why we call it leave-out covariate. And it has lots of advantages, which is it's very interpretable. I think it's very simple. It's not tied to betas. You know, I think I keep asking all my statistics friends, why do you keep worrying about beta? And I think it's because, well, they took their first regression course 30 years ago. They learned about beta, and they've been thinking about beta ever since. I think we're kind of stuck in. So now I'm going to, if I can preach a little bit, you know, I think the way we statisticians, I can criticize statisticians because I am one. I think we learned a bunch of tools, and then when we met the high dimensional world, instead of saying let's try to think differently, we said let's try to add assumptions so that our low dimensional thinking will transfer to the high dimensional world. I really think that's a lot of what's going on. So I think, you know, beta, worrying about beta is to a large degree this fixation on things that we're used to thinking about. This is much simpler. And on a technical note, which I won't have time to talk about, the bootstrap inferences are much more accurate for this parameter than for estimating projection parameters. Okay. I'll try to stop preaching. Sorry about that. It doesn't depend on linearity, model correctness, very interpretable. Let me just mention a brief, some of the literature, and this is not complete at all, but in the true parameter approach, there's some papers by these people. Actually, Victor is going to be here later, hopefully, to talk about some of that stuff, and very fascinating stuff. And again, it's very subtle because it involves these things about to get the confidence intervals. You don't have the usual bias and variance trade-off. The projection or parameter approach, there's the first thing is there's a series of papers by these guys at Wharton. I would really recommend you read their papers. They're very, very nice. Then there's the Stanford group. That's John Taylor and all his colleagues. They have this explosion of papers. I'm going to talk a little bit about this. I think there's something really interesting happening there, but I think there's also some problems. And then I just threw up one of our papers, and there's other people looking at this projection parameter approach. And then we've been working on this LOCO approach, but I also want to mention Giles Hooker and Lucas Mensch, who have a very nice paper about doing something I would call LOCO. They don't call it LOCO, but it's a sort of leave-out covariate thing and they're doing something very clever. They're doing random forests. They're treating the random forest as a U statistic of what's called an infinite degree U statistic, and trying to develop central limit theorems for doing that kind of inference. So and I'm sure there's lots of other people doing all these things as well. So I wanted to try to go through now some of these techniques in case you haven't seen them and explain them and say what I think are the strengths and weaknesses. Before I describe them in detail, here's a table. So this kind of summarizes everything. The first method I'm going to talk about is what I would call debiasing. It treats the beta as if there's a true beta. It's based, however, on very strong assumptions. It does give accurate intervals. I think they're order 1 over root n, and they're very computable. But in terms of robustness, I put no, meaning it's very sensitive to the model assumptions. Then there's the Stanfordian approach or conditional approach, which is based basically on conditioning on the selected model and then using sufficiency arguments to develop a pivot. I'll explain that in a minute. Assumptions are quite strong. The accuracy is unclear to me because sometimes they're actually infinite, these intervals. But they're very computable. They've worked hard to get computable things. Again, the assumptions, they're weaker than the debiasing approach, and in particular, they're not assuming a true linear model, but there's still some strong assumptions. There's what I'll call the uniform approach, which is basically looking over all possible models you can select. And that's the Wharton approach. It's more robust. It's a bit less accurate in return, but it's not clear to me, as I'll explain, that you can do it in very high dimensions. And then there's the oldest method in the world, sample splitting. And everybody knows this, right? You fit the model on half the data, then you do the inferences on the other half. Everybody seems to hate that method, but I actually think it's the best method because it makes virtually no assumptions. I'm a big fan of sample splitting, and it gives very, very accurate inferences. So ironically, you actually get more, people say it's less accurate. You actually get more accurate inferences than you get. So for example, I won't have time to talk about like bootstrap accuracy and so on. You do get more accurate inferences, but how can that be? Well, you could be estimating, though, a less accurate model. In other words, I might choose a poorer model when you only use half the data to select the model. So I'm losing something by sample splitting. But what I'm gaining is the model I've selected, I can now infer very, very accurately. So there's an interesting, I call it the prediction inference trade-off. You're going to predict a bit worse, but get more robust and accurate inferences. This is all explained in great detail in this paper I'm promising to post soon. All right. Then if I have time, I'll talk about a completely different approach that comes from machine learning world called conformal things, which is completely distribution free, but my prediction is I won't get there. I think it's unlikely I'll get to that method. So I kind of broke it down into these 5 or 6 methods. Then there's what I call the forgotten methods, which everybody seems to have abandoned, which is, again, from the olden days, which is we could avoid all of this if we just did unsupervised dimension reduction first, like PCA or variable clustering. Then you're back to low-dimensional regression. You don't have any of these complications. And I think that's worth revisiting those things, but I won't talk about that. Okay, another conceptual issue is what do we mean by coverage? When you say, what's the probability that your interval covers the truth? And I think actually this is something economists are much better at than statisticians, is being careful about what they mean by coverage. Statisticians, I find, are often very loose about this. So the ideal coverage is that the probability that theta is in the confidence interval, in the frequentist sense, and theta here could be random itself. I want the inf of that over every possible distribution to be at least 1 minus alpha. That would be the ideal confidence interval. And as we'll see, there's an order statistic version of LOCO which actually satisfies this property, even in high dimensions. Then there's a weaker condition which I think Lee called, was the person who named it honest inference, and I see it used now and then. Basically what it says is, okay, maybe the first one's too hard. Let's look at the inf of the probability that theta is in C over, and a big is supposed to be a very large non-parametric model, and we'll take the limit of that and demand that be 1 minus alpha. And that's often achievable when the first one isn't. And the important thing is that the inf is on the inside, not on the outside, because that means you're really getting coverage that doesn't depend on the particular distribution. Parametric would be the same thing but with a small model instead of a big model. And yeah, so that's less desirable. Point-wise is just for a particular p, it converges to 1 minus alpha. The problem with that is how big does n have to be before you get close to 1 minus alpha could depend on the distribution p, and you'll never know if you're close or not. What we really want, though, this is another point that I push on, that I argue. So one of my best friends is Rob Tibshirani at Stanford, and he's part of this other approach, and so we're arguing continuously about this. And so he would say this is too strong, but I call it robust and honest. So it's got the inf over all distributions, or a big set of distributions, but you notice there's another inf, and the inf is over all selection procedures, like how you selected the model. This is a controversial issue. Is I think really you want confidence intervals that are valid no matter how the person picked the model. Whereas some people say, no, if we're using the Lasso, you only want it to be valid over Lasso. The reason why I want that is because in real life, nobody sits down with a data set and says, I think I'll apply the Lasso, get 17 parameters, and do my inferences. When I'm analyzing a data set, I plot the data, I look for outliers, I do transformations, I do all kinds of stuff to the data before I actually end up with a model. And how can I write that down as some well-defined rule? I mean, I don't think you can. And I think if you don't have, so in other words, I'm saying the selection rule is actually a very nebulous, complex thing. And this is where a lot of unconscious biases come in. And there's always talk about the irreproducibility of science these days, and I'm not saying this is the cause of it, but it's certainly one part of it, I think. And it's interesting that I think in this theoretical computer science literature, they're doing something now called adaptive data analysis. It's worth looking at that because it's very similar to what we're talking about here. And they also take this point of view that their inferences should be robust to no matter how the model was selected. And I'm very sympathetic to that point of view, but again, I seem to be an extreme point here. All right, so that's the background. Let's start talking briefly about all these methods. So I'm calling them debiasing. There's really a whole class of methods here, and I'm just going to give you an example of one of them. This one's by Javanmard and Montanari. And it kind of works like this. There's no model selection involved. What they do is they just fit a model, say by some sort of sparse fitting thing, so like the Lasso, and you get beta hat. Now the problem is that the Lasso gives you a sparse estimator, but it's biased. So they do this debiasing step. So basically you take beta hat and you replace it with beta hat minus something. The details I guess aren't so important, but you do have to estimate the inverse covariance matrix somehow. That's involved in this debiasing thing. And then when you do that, magic happens. If you take root n beta hat minus beta, and really I should be writing beta hat sub j minus beta sub j for one element, you do get something which is normal plus something of smaller order. So you get this nice central limit theorem, which means now we can construct the usual confidence intervals. So I think this is really clever. And if you wanted to do this over all parameters, of course, you'd have to Bonferroni or something over all models. Or if you'd selected a model, I guess you would only have to Bonferroni maybe over the selected ones, although that's not clear because that's a random selection. But at any rate, it does give you these very nice confidence intervals. Very clean method. But, so let's go through the assumptions. It assumes that the linear model is exactly correct. It assumes these incoherence assumptions, which are often made in high-dimensional regression, which is basically that all these covariates are very close to being independent, which I have a hard time with. It assumes the model is sparse, that there's only a small number of non-zero betas. It assumes the variance is constant. And it requires a very carefully chosen tuning parameter. So theoretically, I find this actually a very appealing and interesting method, but I'm not sure I would want to base, like if I was working with a physician and trying to make decisions, like for example, I work with a biologist. I'm not sure I would be telling him what wet lab experiment to do next based on something that came out of this. I'm not sure I would trust it. Now, what's really interesting, probably the most conceptually interesting thing, is this stuff that's going on at Stanford. It's John Taylor and his colleagues. I didn't list all their papers. They have they're writing papers like one a week, so you can just Google that. So this is really interesting. So first of all, they give up on the linearity assumption, which I like very much. And their target is this projection parameter, the best linear parameter. Now they do have a lot of assumptions. They are going to assume that the errors are normal. They're going to assume that the variance is constant and that it's known. And they're also going to assume that the covariate is fixed in what they do. So now they select a model by some method. I'll say the Lasso, but it doesn't have to be the Lasso. And again, they're going to focus on the projection parameter, the best beta for that selected parameter. And let's just focus on one of them, say beta S of j. And then they make the following very interesting observation. They're going to choose an event E very carefully. Roughly speaking, you can think of this event E as the model you chose. So let's say I chose variables 1, 2, and 8. They're going to condition on the fact that you chose models 1, 2, and 8. Now that's not exactly true. The conditioning event's a little bit more subtle than that. But morally, they're just conditioning on the selected model. So here's what happens. So something very, very interesting happens. Let's look at one of the beta j's. So we have this beta j in this selected model, and I'm just forming the usual pivot. And what is the distribution of that conditional that I've selected variables 1 and 2? Well, if we started with everything kind of normally distributed, now we're conditioning on some event. Roughly speaking, it's going to be like a truncated normal distribution. And in particular, the distribution generally would be something that depends on the whole distribution, right? Even though we're only looking at this parameter, its distribution, its law, could depend on all the parameters. But by the conditioning does something else. It's by sufficiency, it ends up only being a one-parameter family. So we get like a truncated normal, and it only depends actually on this parameter. And this is also because sigma is known. So if you take a truncated normal and take its CDF, I have a CDF. It's actually a family of CDX indexed by one unknown parameter. No problem. We just treat that as a pivot. We just evaluate the CDF for every possible value of the true parameter. That gives us a test, and you invert it. You just do test and invert. I mean, in principle, you can always test and invert anything, right? It's a very general method. But usually, you'd have 10 billion nuisance parameters, and it would be a huge confidence set and so on. But because of the assumed parametric model, this conditioning event has the property, again, because of sufficiency, that it reduces it to a one-parameter family of distributions. And there's a lot of interesting, if you look at the papers, it's all done geometrically. It's all very, very fascinating. But it leads to something you can now compute, because it's a one-dimensional family. You test and invert it. And it has these very strong advantages, which, again, they're not assuming the model is linear at all. And there's no incoherence assumptions, no independence assumptions on the design matrix. So that's very, very nice. That's the nice things about it. The disadvantages are, it is assuming normality, constant variance, known variance, and also there's a problem which I call fragility. And I'll be honest with you, John and Rob at Stanford will not necessarily agree with me about this. So this is my opinion. But I think it's very fragile because it's not just depending on the normality, but it's depending on the tails of the normal. And let me explain why. Suppose you had 1,000 variables, and you just did one step of forward stepwise regression. So what are you doing? You're finding the correlation between y and x1, y and x2, y and x3. What variable goes in first? The most correlated one. So where are you in the tail of that distribution? You're always, in that distribution, you're always in the tail. And now if you ask, what is the distribution of, let's say you pick variable 1. So what's the distribution of the correlation between y and x1 conditional on the fact that that correlation was bigger than all the other ones? That's the truncated distribution you're dealing with. Your p-value is a truncated distribution in the tail of the distribution. You're comparing two tail probabilities. So let me draw a picture of it. You've got this distribution, and you're conditioning on this event, basically that I chose this model. So the conditioning event is this thing. Now when I compute that CDF, that truncated CDF, I have a value of my test statistics, say it's here. And so my p-value is, roughly speaking, the ratio of this to this. But you can see, remember, I'm like 10 to the 6 standard deviations out into the tail. And I'm very nervous about comparing tail probabilities of these normals. And in particular, if you tried to say, well, won't the central limit theorem say everything's approximately normal? Sure, in the center, but there's no central limit theorem that tells you that the tails behave approximately normal. So that's what I call fragility. Whether it's a real problem in practice is something we're not sure yet. I'm just starting a project with my colleagues Ryan Tipshirani and Max Gazelle and some other guys, where we're going to do a really thorough simulation study about these kinds of methods and compare them and see how non-robust they are. But just to give you an idea of how sensitive things are to the tail, here's two distributions. One's a normal, and one is so close to normal you can't tell the difference. But if you compute a ratio of tail probabilities, like say this divided by this, and look at that as I move the event, you can see that that thing is, you can get that's the p-value function. You can get completely different p-values when you're in the tail of the probability. Another way to look at it is, if you look at this, when you're conditioning on the model, so think of these different sectors as different models you're conditioning on. And your p-value is just, in the end, is just some function over the sample space, but it's different depending on which model you're conditioning on. And if you actually look at the pivot, you're computing that's supposed to be, has a uniform distribution, the function looks like this. It's kind of smooth in here, but at the boundary of every model, it's non-differentiable. And so you're computing, the function you're using to do the inferences is this really bizarre thing with all these sharp corners on it and so on, which suggests again that this is not going to be a very robust method for doing inference. In fact, if D was fixed, if you really did fix the dimension, you could just say, look, central limit theorem says everything's normal. This is just a continuous function. It's not differentiable, but it's continuous. So by the continuous mapping theorem, the p-value is uniform. But we have a paper where we look at this, another archive one. You know, refereeing is so slow in statistics. All my papers are still on archive. That if the dimension increases, if d over n goes to infinity and epsilon is not normal, then you do not get, the pivot does not converge to a uniform 0, 1. In fact, we have an example where it converges in probability to 0. Well, actually, it converges to 0 with some fixed probability. So there's some issues there about the tails and the robustness. Having said that, those are technical things. The basic idea, though, about trying to condition on what you've actually selected, I think is very attractive, and there's something important there. So maybe there's a robustified version of this that would work much better. I think that's an interesting open question. Uniform methods. And this is the approach that's been pushed by the Wharton guys. I shouldn't say guys. Linda Zhao's there, so I should say Wharton people. Roughly speaking, the thinking works like this. Suppose I could say, here's all the possible models I could select. So just to have a concrete example, I'm going to do forward stepwise selection with a maximum of 20 variables. So now I can say, OK, all subsets of size at most 20, that's my script S. In principle, if I could now look at the CDF, which is beta hat of S, that's the beta hat for the selected parameter, minus beta S, that's the projection parameter. And if I look at the soup of that over all the models I could select and get this CDF, if I knew that CDF, that would give me uniform inference over all possible models. And in particular, if I now select one randomly using some method, it's automatically correct because it's uniform over all models. And that's what they do. So if I knew that CDF, I would just take, say, my beta hat plus or minus the tail probability there, and you would automatically have a valid confidence interval. So the advantage here is there's no linear model, there's no incoherence assumptions, and it's got what I called honest coverage, as I described earlier. The disadvantage is, how are you going to estimate this? You could say, well, can't I bootstrap this? But think about bootstrapping it. At every bootstrap, every time you bootstrapped, you'd have to take the soup over every possible model you could select. And you'd have to do that on every bootstrap sample. And those are NP hard problems typically. So it's computationally infeasible. So how do they do it? Well, they say, well, let's assume that the data are normal, constant variance, known variance. And then they can actually, they found some ways to compute this. But even then, the last time I talked to Andreas, I think he said maybe they could do 12 variables or something like that. So this is quite limited at this point. Now, maybe there'll be some breakthroughs, but I think there's a serious computational bottleneck here. Now, my favorite method and the oldest one is sample splitting. I don't know, everybody rolls their eyes at this, but I think we shouldn't write it off. I tried to trace the history of sample splitting because people have been doing this for so long, and it's kind of hard to trace it because I think people just do it and don't write about it. But I found references to Hartigan 69, Moran 73, and so on. Here's maybe if anybody else has other references, let me know. I liked Barnard's quote. This is in 1974. He says, the simple idea of splitting the sample in two and developing a hypothesis on one part and testing the remainder may perhaps be said to be one of the most seriously neglected ideas in statistics. And here it is, 2016, and I kind of think that's still true. And so actually the paper that we're going to post on the archive in the next week or two is a kind of a modern look at sample splitting. We kind of want to revive interest in sample splitting. But it's very simple. I'm sure you all know it. You just split the data into two pieces. You do whatever you want from the first data. You select the model with an arbitrarily complicated selection procedure. Then on the second half, the data are independent. So you do whatever you want. Maybe you just fit least squares and use the normal approximation or the bootstrap or whatever your favorite tool is. And that's it. Life is easy. And that's, again, that's automatically both honest because it has this inf over p, but it's also robust because it does not depend on what you did to select the model. So I love that. No assumptions, robust to the selection rule. Now, there is this concern that in the first step, you're only using part of the data to select the model, so you may not pick the most predictive model with the lowest prediction error. And in our paper, we explore this to some degree, but frankly, there's a lot of open questions there. So how to explore this trade-off between prediction accuracy and inference robustness is still something we're really thinking about, and it's a serious issue. It can make a big difference. And you can combine this with any parameter. So in particular, here's the LOCO parameter I talked about. But before I had the mean, why not use the median of that distribution? And the beauty of that is if you do sample splitting and if you use LOCO, which is a better parameter, and if you use the median instead of the mean, you actually can, getting a confidence interval for a median, you can do using order statistics, in a distribution-free way. This is the only method I know for doing high-dimensional inference and regression where you can actually say that it's not asymptotic and there's no assumptions on p. For all distributions p, all selection rules w, the coverage is 1 minus alpha. That's a pretty good, claim, I think. And it's simple. I mean, this is something you can, run pretty quickly. So as I say, we're doing a big simulation study because until we do lots and lots of cases, we're not going to convince people to do this, I think. Let me just talk a little bit about the subsampling approach of Mensch and Hooker. And again, I think Susan will tell you about her approach to doing random forests with inference for that. This is a little bit different. They fit, this is a very recent paper. It just appeared in JMLR. For those of you who don't know, the leading journal in machine learning is JMLR, Journal of Machine Learning Research. And all their articles are free online, as should all. I don't know what the state of economics is. I've been fighting this battle in statistics to get all our journals free and online. I don't know what happens in economics, but ML, as usual, is ahead of us, and they're doing it the right way. All right, so what they do is they say, well, what is a random forest? You're getting these trees, and you're averaging things, and each one is built from a subsample of the data. So what have you got? You're just taking an average of, why am I pointing here? I'm taking an average of subsets of the data. Well, that's just a U statistic. Now, it is an incomplete U statistic. You can't take every possible subset, and this is especially true because typically you let the subsample size grow as you get more and more data. So the fact that you're only taking a random subsample of U statistics actually matters a lot. And that's a incomplete U statistic. There's also the randomness about the covariate selection, so that's another issue that makes it not quite a U statistic. And it's infinite order, which means it's not like a typical U statistic where you're just looking at pairs of data. You're going to let it grow with sample size. So they have a very nice development of a central limit theorem here for incomplete infinite order U statistics. And once they have that, they say, okay, so the mu hat is approximately normal, and they do a test that I would call like a LOCO test. They say they look at the random forest, then they look at the random forest after you've left out some covariates and say, do my predictions change or not? And they have a normal based test because they have a central limit theorem, and it's very interesting. So I would encourage you to take a look at that. The test statistic is just going to be, again, the fitted random forest with and without the covariates of interest. And by the way, I talked about linear models earlier. You could do exactly the same thing for linear models. There's nothing really special to random forests here. So the advantage is this is non-parametric now because it's a random forest. It's not a linear model. It's assumption-free, sort of. If you don't like the splitting, this avoids the splitting. There are some questions that I've been thinking about, which is, for one thing, it doesn't return a simple model. Whether that bothers you or not, I don't know. Some people don't care, which is great, but some people want to have an interpretable model, so I guess it depends on the application. The central limit theorem here, there's a technical issue, which is the central limit theorems I was talking about earlier are uniform. I don't think this one is, although it's not clear yet. It hasn't been worked out. So I think there's some more research that needs to be done to understand how strong the inferences are here. Okay. Oh, I'm mentioning Susan and Stefan's paper here that does a different approach. What should I talk about? Let's talk a little bit about, I guess I won't get to anything about causation, but that's okay because other people are going to talk about causation. I mean, the big issue in causation, all I was going to say about it was you need the extra assumption, of course, that there's no unmeasured confounders. And so that's one more worry, and presumably, there's papers about doing sensitivity to unobserved confounders, and I think an interesting area for future research is, can you take the work that's been done on sensitivity to unobserved confounding and adapt it to these machine learning kind of regression models? That was all I was going to say there. There's a completely different approach to inference that was invented by Vladimir Vok, who is a kind of a machine learning probabilist philosopher, warlord. I just threw in the warlord. I don't know why. I sounded like I was giving a line from Apocalypse Now or something. Anyway, and so the archive is to yet another unpublished paper of mine where we, still waiting for referee reports, where we adapt this to doing high dimensional regression inference. But the idea is beautiful. If you've never seen this idea due to Vok, it's such a simple, beautiful idea. And implementing it can be challenging, but the idea is very simple. And the idea is, suppose you want to get a model-free, completely distribution-free confidence set for a prediction for a future y. So it's very prediction-oriented. You make up a working model, let's say a linear working model, but the assumption at the beginning of this is that the model's wrong, and there's no approximations here. You're going to get exact inferences even if the model's wrong. That's Vok there. And what we're going to get out at the end is a set C with the guarantee that the probability that a future y is in the prediction set is 1 minus alpha for every possible p. No asymptotics, no regularity conditions, nothing. It's really a remarkable thing. And let me explain the basic idea because I'm running out of time. I don't know how far I'll get into it, but it's worth seeing this if you've never seen it before. So I'm going to do it first without covariates. Suppose you just have a sequence of y's, y1 to yn. All right. Now somebody says, I want to predict a new y. Here's the idea. Let's take a guess at what the next observation is. Let's call that little y. Arbitrary. Little y is some arbitrary point. Now I'm going to test the hypothesis that the next observation is equal to my guess. So what I'm going to do is form the augmented data. This is the key step. You take your data set and you augment it with yn plus 1, where yn plus 1 is equal to your guess. So it's a little bit like the opposite of cross-validation. Instead of leave one out, it's add one in. Now you compute some sort of, he calls it a conformity score. We would call it a residual. So for example, just take yi minus y bar, but it's got to be based on the augmented data. And now again, I want to test this hypothesis, but you can see that these residuals, under the null hypothesis, if I've actually put in a true guess that's correct, these data they're exchangeable, and the ranks of the residuals are uniformly distributed. Every observation has an equal chance of being the biggest one or second biggest one. So if I just count how many residuals are bigger than the one for the one I just guessed, that's an exact p-value. That's a uniformly distributed p-value with no assumptions at all. And that was for one guess y. So now I repeat this for every y and invert it. And that's it. Now I have an exact confidence set. And so for any distribution p, any n, that's an exact prediction set. And I shouldn't say a confidence set. I should call it a prediction set. And if you want to know more about this, I should have put up the references. But I wrote a series of papers with my young colleague Jing Lei, where we looked at this from a statistical point of view. So we developed it for density estimation and regression and classification, and we looked at its minimax properties and all that, and we kind of re-expressed it in a more statistical language. I'm sorry, I forgot to put those references. Because the properties of this thing, the correctness is always there, but the size depends on how good your guess of the model is. So this is distribution-free finite sample. You should look also, by the way, if you're interested in this, just Google VOC and you'll find zillions of papers of extensions of this that he and his colleagues have done, which has largely been ignored in statistics, I have to say, which is unfortunate. So in linear regression, high-dimensional linear regression, the basic thing is the same. You have data, you do model selection, you get a beta hat. We augment the data. We have to repeat the entire procedure, but not really. There's some tricks to avoid that. But conceptually, you repeat everything. You get residuals. You get your p-values. In principle, you repeat this for every possible x and y. And what a lot of the papers about is how to avoid doing that. And you get these valid prediction regions. So that's a way of doing inference that doesn't depend on the working model being correct. And I don't have time, obviously, to go through all the details of how you do this in high-dimensional inference. So again, I'm just throwing up a reference for our work on that. Oh, and also, I'm happy to say we have an R package to actually implement this, thanks to my younger colleagues who can program well. That's in Ryan's GitHub thing, whatever that is. But I know if you go there, there's all the R code, including every example we did, and it will reproduce the examples for us. This is like in the spirit of reproducible research. So I think I should, so this is the causal stuff I'm going to skip. I'm going to go to my conclusion. So in conclusion, there are now many methods for doing inference for these high-dimensional machine learning models or statistical models, whatever you want to call them. Whether they're needed or not, I think depends on the application. You may not need to do standard errors or hypothesis tests. On the other hand, I'm guessing in economics, when you're thinking about, presumably you're thinking about like policies and what policies to implement, I assume that probably these things could be very important in some of these cases. Sample splitting, to me, is the easiest and gives the most valid, robust confidence intervals, but you are losing prediction accuracy, of course, when you split it. I want to make a case for forgetting about beta in regression. There's other parameters you can use to describe the importance of features, but not everybody agrees. There's these conformal methods I didn't really have time to talk about, but they're worth looking into if you're interested in this stuff. For causal inference, I really think there is a large literature that you all probably know much better than me about doing sensitivity to unobserved confounding, but I think exporting that to the high-dimensional setting is, as far as I know, not much has been done on it, and I think that's an interesting open question that maybe that's a place where statisticians and machine learning people and economists could collaborate. And with that, I am done. Thank you for your attention.